Okay, this is part 3 of the counting example problem videos. The counting problems we're going to work in this video are a little bit harder than the problems we worked in part 1 and 2. Now, if you haven't watched the previous video on derangements, which is really not so much about derangements, but more about showing a use of the principle of inclusion-exclusion, or how we use Venn diagrams with when you've got multiple events with overlapping outcomes to subtract out certain outcomes from the problem. If you haven't watched that video, go check out that video first, then come back here, because the problems in here in part 3 and in upcoming parts are going to require the use of Venn diagrams, which is one of the reasons why these problems are more complicated. Okay. How many different words, including nonsense words, can you make by rearranging the letters of the word effervescence? Okay, so this is pretty simple. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So we can start with 13 factorial. All right, but now we need to use the division rule. So we've got, let's see, 1, 2, 3, 4, 5 E's. We've got 2 F's. We've got 2 C's. That should be it. Yeah, so divide by 5 factorial, 2 factorial, 2 factorial. So, okay, 13 times 12 times 11 times 10 times 9 times 8 times 7 times 6 times, and that's it. The 5 factorial is gone. And then 4 down here. So, okay, 13 times 12 times 11 times 10 times 9 times 7 times 6 times 2. How many different 4-letter words, including nonsense words, can be made from the letters of effervescence if letters cannot be repeated? Okay, so once again, we've got 5 E's, 2 F's, and 2 C's. Okay, so we've got a 4-letter word. Now, letters cannot be repeated. So all we need to do here is think about how many unique letters do we have. So it's 13 total. But then if you take 13 and, let's see, taking out the E's and the F's and the C's, you've got 4, okay, but then we add an E back, an F back, and a C back. That's 7 unique letters. So it's just 7P4. So 7 factorial over 4 factorial times 3 factorial. So 7 times 6 times 5, and then the 4 factorials cancel, over 3 times 2. So 7 times 5 is 35. All right, how many different 4-letter words can be made from the letters of effervescence if letters can be repeated? Okay, so once again, we've got 5 E's, 2 F's, 2 C's, okay, 4 letters. All right, now, so unique letters, there's 7. You've got E, F, S, C, N, V, R. Okay, now we can't just say, treat this as a permutations with repetition problem, where we would say it would just be 7 times 7 times 7 times 7. If all these letters can be repeated, then that's what you do. The problem with that is, yeah, you can have 4 E's, but you can't have 4 F's, you can't have 4 C's, you can't have 3 F's or 3 C's. So what we could do, though, is we could get 7 to the 4th and then subtract out the cases where you would have 4 F's and 4 C's and 3 F's and 3 C's. Okay, so 4 F's, that's just 1. 4 C's is just 1, right? F, 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 C, 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 C. Okay, now what about 3 F's and 3 C's? How many arrangements are there? So, okay, we could have F, 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 and then any other letter here. Okay, so this is there's 6 letters that could go here, right? Because you don't have an F anymore. There's 6 letters that could go here. But then that letter could go here, 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 or here. So it's 6 times 4. So minus 6 times 4. But we could also have that. What if it was 3 C's? So we want to double that. So 2 times 6 times 4. That's 6 times 8, which is 48. So minus 2 minus 48, that's minus 50. And that should be it. Because, again, 7 to the 4th is that we treat this as a permutations with repetition problem. So if there was each of these letters in the word there was 4 or more of their occurrences, then it would be a permutations with repetition problem. You could just pick any of the letters you want, and so it's 7 times 7 times 7 times 7. Okay, but we can do that with the E's, but we can't do that with the F's. So we just have to, so this 7 to the 4th is assuming that we could have all F's, we could have all C's, or we could have a situation of 3 F's in the word or 3 C's in the word. And we subtracted those out. So there you go. 3 kids, Alberto, Bernadette, and Carlos, decide to share 11 cookies. They wonder how many ways they could split the cookies up, provided that none of them receive more than 4 cookies. Someone receiving no cookies is, for some reason, acceptable to these kids. So, okay, you've got these 11 indistinguishable objects. The cookies are indistinguishable, and we're distributing them amongst these 3 kids. So this is that classic combinations with repetition problem, right? Which you could model with the integer summing. X1 plus X2 plus X3 is equal to 11, where these are the 3 bins are the 3 kids. All right, now the only issue here is that we have a restriction that we haven't seen before. We know how to deal with restrictions where it says, okay, all kids must get at least 1 cookie, or like Bernadette has to get at least 2 cookies. We can deal with that, but we haven't seen an upper limit. Okay, well, how do we deal with the upper limit in this case? Well, what we're going to do is we're going to say that, so if we calculate the total number of outcomes with no restriction, so a kid can have 0 cookies, that's fine. So you could have Alberto could get all 11 cookies, Bernadette could get all 11, etc. Well, then that's just the combinations with repetition. You've got the bins are the bins are the kids, but then we're choosing from the bins, right? This is why it can be repeated, and we're going to associate each bin with a cookie. But it's repetition because we could choose Alberto 11 times if we wanted to. But then it's combinations because we don't care if we put Alberto on this cookie and Bernadette on this cookie. We don't care about if Bernadette gets this cookie and Alberto that cookie. It doesn't matter. Okay, so in that case, we know it's going to be, we're choosing from 3, and then we have 3, we're choosing 11. But combinations with repetition. So 11 plus 3 is 14. Minus 1 is 13. Choose 11. So that's the total number. Let me put this over here. The total number of ways you can distribute 11 cookies to these 3 kids, where it's okay if a kid has 0. There's no lower limit, but there's also no upper limit either. You could have a kid gets all the cookies. That's what this count is. All right, now what we're wanting to do is, to get the answer, we want to subtract out the outcomes that we don't need. And so this is where the overlapping outcomes come in. It's really any time where you have a problem and you're saying, okay, to solve this problem, I can kind of get the total number of outcomes in the system, and then I want to start subtracting things out. That means you have overlapping outcomes. And that's where you're going to want to apply the A union B union C, etc. You want to break it down that way with the Venn diagrams. Now, just to point out, if we come back to the previous problem, we did have this kind of language here in the sense that we started with this 7 to the 4th, right? That was all of the ways you could, it was the permutations with repetition, right? For seven distinct letters. But then we wanted to subtract, we were subtracting out outcomes we didn't want, right? So why didn't we do a Venn diagram here? Well, we could have. However, if we would have broken this down, what we were subtracting out is the cases where we had 3 or more F's or 3 or more C's, right? That's what 7 to the 4th was. Yeah, 7 to the 4th was also counting. It was counting cases where we had 3 or more F's or 3 or more C's, right? So if we do the Venn diagram in that case, then, okay, so here's the entire system. All the ways it's 7, that's 7 to the 4th. Choosing from 7 distinct letters with repetition, these letters here, choosing 4 of them with repetition. You could use any of them however many times you want. I mean, up to 4 times because you're choosing 4. All the different words you can have. 4-letter words, including these like nonsense words, right? That's the system. So now, what events are we analyzing within the system? Well, we're analyzing usually the way this is going to work is usually you're solving for like A union B union C, whatever. That's what you want. Usually that's what you're looking for. And these are the events you're trying to subtract out. That's why you're looking for this. So you're saying, okay, because the reason why this is what you're looking for is because A could be overlapping with B and overlapping with C, but the union removes the duplicates. That's why you're looking for this, right? Because you have this overlapping events, but you want to take out the duplicates. That's exactly what the union is. All right, so what are we looking for? Like, what are we trying to subtract out here? We're trying to subtract out all of the words within this system that have F 3 or more times or C 3 or more times. Well, those events aren't overlapping, right? Here's the F and the C. You can't have 3 or more F's and then at the same time have 3 or more C's and vice versa. So that's why we didn't use the Venn diagram here. Okay, now, but here it's going to be different. Because, so we've got, if we draw this, so we have our entire system of all of these outcomes here, right, where, you know, Alberto gets 11, Bernadette gets 11, Carlos gets 11, whatever. All right, now, what are we trying to, what's the union of sets we're trying to take out of here? We're trying to subtract out. So it's when Alberto has 5 or more cookies, or Bernadette has 5 or more cookies, or Carlos has 5 or more cookies, or a combination of those, whatever, right? So we have to think about, so here's the case where all the cases where Alberto has 5 or more cookies, we'll put an A. Okay, now, what about the case where Bernadette has 5 or more cookies? Well, that can overlap here, right? That can overlap. You can have Alberto and Bernadette have 5 or more cookies. You can have Alberto and Carlos have 5 or more cookies. So all of these could be overlapping. Now, just to note, though, if you're not sure right off the bat, if you're not sure if the sets are overlapping or not, then you could just put them all overlapping. We could have done this here. I could have just made these sets overlapping and then gone through the whole derivation. And then when it came time to analyze, okay, what is F intersection C? I could have thought about it at that moment, and the numbers would have worked out, right? Just because you put them overlapping in the diagram, as long as when you can go through the whole formula and figure it out from there. So it's probably good practice to just, unless it's blatantly obvious, just go ahead and if you don't know, if it's not blatantly obvious, just make all the sets overlapping. Especially if you've got like 4 or 5 events, well, then just assume they're all overlapping, and then you're going to go through the formula and analyze the different regions as you go. And if you realize they're not overlapping, you'll put 0 for those 2 events. So, okay, here's where you've got Alberto has more than 5 or more cookies, Bernadette and Carlos. Okay, so now we've got that. We can already tell we can't have all 3 have 5 or more cookies. So this is going to be 0 in here, right? I can go ahead and put that. Okay, so we're trying to solve for the number of elements in A union B union C, because that's what we want to subtract out from the system. This is our answer. This is our answer. We're trying to subtract out this, but we don't want the duplicates. That's the problem. That's the confusing part. And that's why we need to get the union here. Okay, so we know this is the number of elements in A plus the number of elements in B plus the number of elements in C minus the number of elements in A intersection B minus the number of elements in A intersection C minus the number of elements in B intersection C plus the number of elements in A intersection B intersection C, which is 0. So this is what we're looking for. Okay, what's the number of elements in A? What is all of the ways where Alberto, the number of outcomes where Alberto has 5 or more cookies? Well, okay, you've got so 1, 2, 3, 4, 5. There's Alberto. Now you're left with 1, 2, 3, 4, 5, 6. But order doesn't matter here. You could put these 5 Albertos wherever you want. It doesn't matter. So all we're asking is now choosing from A, B, C. We could make Alberto have get the rest of the 6 cookies. It doesn't matter, right? What's the number of combinations for these slots here, right? It's going to be combinations with repetition here. Let's see, 3 choose for 6 slots. Combinations with repetition. So 6 plus 3 is 9. 8 choose 6, right? But like we're multiplying by 1. There's only one way to choose 5 Albertos, right? So, okay, 8 choose 6, but what's B going to be? What's the number of elements in B going to be? It's the same thing. Because then you're just changing it to, okay, there's 5 Bernadettes. It's the same thing. So this is just 3, A plus B plus C is 3 times 8 choose 6. Okay, great. Now, what about A intersection B? So you have Alberto and Bernadette have at least 5 cookies. Yeah, so note that this accounted for Alberto having 5 cookies, but he could have had 10, could have had 11. It accounts for everything, right? So what if now we've got Alberto and Bernadette have 5 or more cookies? Well, okay, you might wonder, well, don't we have to count if, maybe Bernadette goes first, the 5 Bernadette cookies go first, the 5 Alberto cookies go second? No, this is one outcome here where Alberto has 5, Bernadette has 5. It doesn't matter how they're mixed, right? It's just a matter of, okay, what can be here? Well, there's 3 different options. This could be A, B, or C, right? This is just 3. There's only 3 ways where you can have Alberto has 5 or more cookies and Bernadette has 5 or more cookies. It could be the case where Alberto has 5, Bernadette has 5, and Carlos has 1. It could be the case where Alberto has 6, Bernadette has 5. It could be the case where Bernadette has 5, Alberto has 6. So there's 3 here. Okay, so this is 3, but then this is 3, and this is 3. So what you've got is 3 minus 3 minus 3, you have minus 9. And there's A union B union C. So now the final answer is 13 choose 11 minus, and then A union B union C. So minus 3 times 8 choose 6 plus 9. A bag contains beads of two colors, black and white. What is the smallest number of beads which must be drawn from the bag without looking, so that among these beads there are two of the same color? Okay, so the smallest number of beads, the smallest number of something happening so that something happens. This sounds like a pigeonhole principle problem, right? So what's the total number of objects or people or whatever that need to be placed into these K different boxes, or that's the pigeonholes, to where there's no matter what, assuming that all of these objects are going to go into one of the boxes, they have to go into at least one. They have to pick one. Okay, so no matter what, then every single one of the boxes is going to have at least C of those objects in it. There's no matter what. That's the pigeonhole principle type of problem, and it sounds like that's what this is. So a bag contains beads of two colors, black and white. What is the smallest number of beads which must be drawn from the bag without looking, so that among these beads there are two of the same color? Okay, so with pigeonhole problems, the hard part is to identify what's the pigeonholes and what's the pigeons. So we're going to make the pigeonholes be the color. Okay, black, white. And the pigeons are the beads. So a pigeon comes in, and it's going to have to go in one of the two bins because there's only black and white beads in the bag, right? So you pick a pigeon randomly. It has to go in one of the two boxes. So we don't know what N is. We know what K is. And do we know C? Two of the same colors. C is 2. So, okay, this is N divided by 2. The ceiling function is going to be less than or equal to 2, greater than 1. So N is less than or equal to 4, greater than 2. So the lowest value here is N is equal to 3. So the answer is 3. And that makes sense because the worst case scenario is you pick a black bead first, then you pick a white bead. So now the third pick is gonna have to be black or white. The Notre Dame Model UN Club has 20 members. 5 are seniors, 4 are juniors, 2 are sophomores, and 9 are freshmen. In how many ways can the club select a president, a secretary, and a treasurer if every member is eligible for each position and no member can hold 2 positions? So a president, a secretary, and a treasurer. Okay, so we're picking from a group of 20 members, and it doesn't matter if we pick a senior, junior, whatever. The seniors, juniors, sophomores, freshmen doesn't come into play here. We can pick anybody. We just can't pick the same person twice. So it's a permutation with just a standard permutation problem with no repetition. So you're picking from 23, right? Because you pick one, now you can't pick the same one again. So it's 20 times 19 times 18. That's what 20p3 is. But you do want to count, though, if you have, like Philip comes here, Tim comes here, and those switch, you count that, and that's what the permutation does. So 20p3. And how many ways can the club choose a group of 5 members to attend the next Model UN meeting in Washington? So sounds like the order doesn't matter, and you're just picking from the group. We're not considering, it doesn't matter if it's a senior, junior, whatever. Just pick 5 from the group. The order doesn't matter, so that's 20, choose 5. There's no repetition or anything. You can't choose the same person twice, so okay. And how many ways can the club choose a group of 5 members to attend the meeting in Washington if all members of the group must be freshmen? Okay, well, that's still easy because now we're choosing from the freshmen. There's 9, so it's 9, choose 5. Okay, and how many ways can the group of 5 be chosen if there must be at least 1 member from each class? So, okay, we've got the, let's see, 1, 2, 3, 4, 5. And so you need to choose. So, okay, we can look at it this way. We've got we can just say, we can look at this here, these 4, as just it's not even a permutation combination problem. We're just choosing from, okay, we've got 5 seniors, then we've got 4 juniors, then we've got 2 sophomores, and we have 9 freshmen. Order doesn't matter here because you can't put one of the seniors here, or you can't put one of the juniors like here. These are distinct groups we're pulling from, right? The only issue is that now we come here, and this is like dynamically related to this a little bit, right? Now we've chosen 4. So now we've got 16 options to choose from. So, okay, there's 16 different options. However, the only issue, we have to be careful because, who these 16 people are depend on who we picked here. Okay, so let's try and think about this. Maybe we could use the Venn diagram to help us out. So this is, you've got, this could be anybody, any one of the seniors, juniors, sophomores, and whatnot. So if we just reported this answer, 5 times 4 times 2 times 9 times 16, what are we double counting here? Or are we double counting anything? So, okay, we could have, let's say the group, within these groups, we've got Jack, Casey, Alex, Scotty. Okay, so that's a senior, junior, sophomore, freshman. And then over here, we've got Logan. Okay, the issue is that where did Logan come from? Was Logan is going to be a senior, junior, sophomore, or freshman. Let's say Logan was a junior. Okay, then in that case, we're also counting, was this Jack, Logan, Alex, Scotty, Casey? Do we want to count both of those? Well, no, we don't, because we're treating this as a combinations problem. It's just like the previous problems. We're saying 1, 2, 3, 4, 5, just a group of 5, or it doesn't matter. So we don't want to count that reordering. Okay, so that makes sense, but now what do we need to divide by then? Well, for each of the 16 potential people we put here, we can see that it's going to, so okay, we put Logan, let's see what happens if we put Logan here. We put Logan here. Now, what's this multiplication doing? Okay, it's saying Logan's there, and then it cycles through all of these where order doesn't matter, right? All of those with Logan, that's what we want, okay? But then it also swaps out whatever group Logan came from. And it could have been, let's say Logan came from Logan's only going to come from one group, so it's going to swap out the group Logan came from with the person in that group. So it's just we just want to divide by 2 because it's just double counting it once for each person here. So we just divide by 2. So the result is the 2 goes away. We've got 16 times 9 times 5 times 4. Okay, show that in any group of 5 people, there are 2 who have identical number of friends within the group. Okay, so this sounds like a pigeonhole problem. So I'm assuming that every person's going to have a friend, at least one friend. Okay, so you've got these 5 people. So again, the challenge with a pigeonhole problem is identifying what are the pigeons, what are the pigeonholes, and then how many pigeons and pigeonholes are there? That's the challenge. So we can, let's see. We could say, I mean, it's tempting to say the people are the pigeons, right? But remember, you have to be flexible with that. It doesn't matter what you make we could make the people the pigeonholes. If it just whatever works. So, but yeah, I mean, we can start by thinking about the 5 people are the pigeons. Let's just start there. And then so C is going to be 2. C is going to be 2. Okay, the pigeonholes are going to be, how many friends do you have? Right? We're going to take this person and say, okay, does this person have, within that group, does this person have 1 friend or 2 friends or 3 friends. So at most, a person can have 1, 2, 3, 4 friends. Right? So this is 4, 1, 2, 3. So here's this person. We put them in Pigeonhole. If it has 2 friends, right? Put them in Pigeonhole 2. Okay. So now the question is, we've got 5 pigeons, 4 pigeonholes, or, yeah, we don't know. Well, okay, yeah, we don't know. We have to prove that C is equal to 2 or more. We have to prove that. So, okay, if we have 5 pigeons and 4 holes, assuming everyone's got to go in one box, everyone has 1 friend, what's this equal to? Well, this is going to be something greater than 1, between 1 and 2, so this is 2. There you go. That makes sense, because the worst case scenario is you spread them out as much as possible. Now we've got 1 left. Someone's going to have to go in one of the boxes. From an unlimited selection of 5 types of soda, one of which is Dr. Pepper, you are putting 25 cans on a table. Determine the number of ways you can select 25 cans of soda. Okay, so an unlimited selection implies repetition. Okay, so you've got these A, B, C, D, E. You can choose however many you want from each of these, and you're picking out 25. Right? But you could pick all 25 Dr. Peppers, all whatever, all A's if you want, right? So what's the number of ways you can select the 25 cans? Okay, but the next question is, does order matter? And no, it doesn't. So it doesn't, I mean, maybe it would, but the only way order would matter would be if they were saying that, so we chose a Dr. Pepper here, a Sprite here, a Coke here, but like all we're doing is saying, okay, how many Sprites did we choose? How many Dr. Peppers did we choose? That's all we're saying, right? So we could choose all 25 be Dr. Peppers, or all 25 be the other soda, etc. We could choose 10 of them be Sprite, 4 be Dr. Pepper, etc. We don't care which one we chose in what position. So, okay, that's just then. We have combinations with repetition. So we're choosing from a group of 5 and taking 25. So 25 plus 5 is 30. So 29, choose 25. Okay, determine the number of ways you can select 25 cans of soda if you must include at least 7 Dr. Peppers. So 7 are going to be Dr. Peppers. So that's D. Right? So all this is just, we kind of went over this idea in a previous problem. All this is just, okay, we've got 18 slots left, and we could choose from 5. It's going to be choose from 5, 18 slots left. We could choose the rest to be Dr. Peppers. It's whatever. It doesn't matter that, oh, well, don't we have to account for the ordering, all these are just, we're only counting one configuration of the 7 Dr. Peppers, right? We have to count the other configurations. There is no other configurations. We don't care where these 7 Dr. Peppers are distributed within the other 18. It's combinations, not permutations. So, okay, 18 plus 5 is 23. 23 minus 1 is 22. So 22, choose 18. Okay, now the last problem says determine the number of ways you can select 25 cans of soda if it turns out there's only 3 Dr. Peppers available. So it's not a true combinations with repetitions problem, because you can't choose an unlimited number of Dr. Peppers. Okay, so here's an example where if you're scratching your head, not sure what to do, then it's either an overlapping outcomes or it's like an OR problem. You got to break it down into different scenarios. And that's what this is. We're going to have to count, okay, what if we didn't choose a Dr. Pepper? There's 3 Dr. Peppers, but we could have not chosen a Dr. Pepper, right? That's one scenario. So in that case, we're choosing from 4, 25. So that's 28, choose 25. Okay. We could have just chosen one Dr. Pepper. In that case, we've got, so we're choosing from, we just chose one Dr. Pepper. In that case, for the rest, we're choosing from 4, but there's 24 slots. So that's 27, choose 24. We could have chosen just 2 Dr. Peppers. So that's would mean 4, choose 23 combinations with repetition. So that's 26, choose 23. And if you chose 3 Dr. Peppers, we can see the pattern is going to be 25, choose 22. So it's 28, choose 25, plus 27, choose 24, plus 26, choose 23, plus 25, choose 22. That's the case where you didn't choose a Dr. Pepper, you chose 1, you chose 2, and you chose all 3. And then the rest, you could choose however many of the rest. How many ways can you distribute 10 cookies to 4 kids so that no kid gets more than 2 cookies? Okay, so similar to one of the problems we worked earlier, but now it's no kid gets more than 2 cookies, but then we have 4 kids instead of 3 kids. Okay, so we want to let's think about the total number of outcomes in the entire system. So there's no restrictions. In that case, you've got these 4 kids you're choosing from, where you could choose one of the 4 kids 10 times, and you're choosing 10 slots. So that's 10 plus 4 is 14, minus 1, 13. 13, choose 10. That's the entire system. Okay, now, if you're not sure if there's overlapping events, then it doesn't matter if you're wrong, if they're overlapping or not. You can just assume they're all overlapping, right? So I wish I would have mentioned that right from the beginning, but you can just go ahead and assume they're overlapping, and you'll figure it out as you go. Like if they're not overlapping, then you'll analyze it like A intersection C and realize, no, that's 0. And then then you'll make them not overlapping, right? So we're trying to count, right? What are we looking for? What we want to subtract out here. What we want to subtract out is, we'll say it's A union B, union C, union D. That's what we want to subtract out, where A is all of the cases where the first kid gets 2 or more, or more than 2 cookies, 3 or more cookies. All of the cases where the first kid gets 3 or more cookies, in union with all of the cases where the second kid gets 3 or more cookies, in union with all the cases where the third kid gets 3 or more cookies, and then the fourth kid, in union. So we're removing the duplicates. That's the big key here. That's what the union means. We don't care about the intersections. It's just, look, if A got more than 2 cookies, that's what we want to know that. Or B, or C, or D, but then take out the duplicates. That's what this is. Okay, so we know the formula is, so okay, so now we're gonna subtract the pairings, and so you can to make sure you get the number of pairings right, where we've got these 2 slots, right? So order doesn't matter. With union and intersection, order doesn't matter. So we're choosing from A, B, C, and D. That's 4, choose 2. Right? This could be A, B. This could be C, D. So to make sure we get this number right, what is 4, choose 2? That's 4 times 3 times 2 over 2 times 2. That's 6. So we know that we should have 6 here of these intersections, pairs of intersections. So minus A intersection B minus, let's see, we can do A intersection C minus A intersection D minus B intersection C minus B intersection D minus C intersection D. Is that 6? 1, 2, 3, 4, 5, 6. Okay. So now we want to add the threes. So, okay, we have 4 choose 3. So that's 4 factorial over, it's going to be 3 factorial, so it's going to be 4. We should have 4 outcomes here, or 4 of these intersection of triples. So A intersection B intersection C, then plus, let's see, A intersection C intersection D, plus B intersection C intersection D, and now there's one more. So A intersection C intersection D, no, we already did that. A intersection B intersection D. Yeah, A intersection B intersection D. Okay, now then we want to subtract A intersection B intersection C intersection D. So there we go. Now, let's just start filling this out. So, okay, what's the total number of ways that one of the kids could have 3 or more cookies? Well, okay, we know how to do this. This is what we've been doing for the other problems. It's just going to be, you've got, so there's 3 or more cookies, so at least 3. So that leaves 7 slots. You're choosing from 4 kids. Combinations with repetition. So that's 7 plus 4 is 11, minus 1 is 10, so 10 choose 7. And that's going to be the exact same thing for B, C, and D. So what we've got is 4 times 10 choose 7. Okay. Now, let's see. What about like A intersection B? That's when you've got 2 kids have at least 3 cookies. So we would say there's 6 slots already gone, so you're left with 4 slots. And so you're choosing from a group of 4 kids for 4 slots. So that's 7 choose 4. And there's 6 here, because this could be the same thing. So 6 times 7 choose 4. Okay. Now, for an intersection of 3, we've got, so 3 kids have 3 cookies at least. So that's 9 slots are taken. You're left with 1 slot. So you're choosing from 4 kids for 1 slot. So 4 plus 1 is 5, minus 1 is 4. 4 choose 1. And there's 4 of these. So 4 times 4 choose 1. So that's A union B union C union D. So let's go ahead and get this number. Okay, 4 times 10 choose 7 minus 6 times 7 choose 4 plus 4 times 4 choose 1. 4 times 10 choose 7 minus 6 times 7 choose 4 plus 4 times 4 choose 1 is 286. Okay. So we want to subtract this out from 13 choose 10. So what is 13 choose 10? It's 286. So what's that telling us? That's saying that the answer here is 0. Like, how many ways can you distribute 10 cookies to 4 kids so that no kid gets more than 2 cookies? There are no ways you can do this. So does that make sense? Well, yeah. Because you've got 4 kids, and you're going to have to give a cookie to a kid no matter what. There's no way you can spread it out. 2, 2, 2, 2. You're left with 2 more cookies. Someone's going to get more than 2 cookies. Harry Potter's closet contains 12 numbered brooms, of which 8 are Comet 260s, numbered 1 through 8, and 4 are Nimbus 2000s, numbered 9 to 12. Harry, Ron, George, and Fred want to sneak out for a game of Quidditch in the middle of the night. They don't want to turn on the light in case Snape catches them. They reach in the closet and pull out a sample of 4 brooms. Okay. How many different samples are possible? So a sample of 4 brooms. It just sounds like they're saying order doesn't matter. Just 4 brooms in whatever order. So in that case, we've got, there's no duplicates here. There's no indistinguishable objects. They're all numbered. So we're just choosing from a group of 12 different objects, right? It's not like you have 2 brooms that are the same or something. Okay, so, but the order doesn't matter. This is 12, choose 4. Okay, how many samples have only Comet 260s in them? So we've got the 12, choose 4 is the total number of samples. How many have only Comet 260s? So, okay, we're choosing from this group of 12, right? And they're saying of all of these 12, choose 4, how many are only these Comet 260s? So the way we can think about this is, so it's going to be, let's see, 8, choose 4 is going to be the answer. The reason is because, let's say we start picking. If we choose, in any case where we choose at least just 1 nimbus, then we're just ignoring that, right? Because it's not a part of our count. We're just saying, look, for the cases, if we went through and did all of these picks, right? Like hypothetically, all of these took place. For the cases where we happen to choose, all 4 are Comet 260s. Then what are the different outcomes in those cases? It's 8, choose 4. That's it. Okay, how many samples have exactly 1 Comet 260 in them? So, okay, we're choosing from 12. We're ignoring all the cases where we don't choose a Comet 260 or we choose more than 1 Comet 260. All of the 12 choose 4 cases that don't, where we choose more than 1 Comet 260 or don't choose a Comet 260, we're ignoring those cases. So, we chose a Comet 260. Let's say that's what this A is. So now the question is, what are the possible outcomes here? Well, okay, we have 11 left, right? It's going to be 11, choose 3. Now, okay, but do we need to divide by something, multiply by something? Because what if the A was here or here, here? That doesn't matter. Oh, wait, no, I'm sorry. That's not right. I'm sorry. No. Okay, we chose the Comet 260. Now, for the cases where we don't choose another Comet 260, then we're picking from a group of, let's see, it's a group of 4 Nimbus 2000. So it's 4, choose 3. 9, 10, 11, and 12. This could be, yeah, so, okay, this could be broom number, this could be broom 3, this could be broom 9, 11, and 12. There's one outcome. But it doesn't matter if you switch 9 and 3 here. That doesn't matter. This could be broom 9, 11, and 10. There's another outcome. Okay, but for every 9, 11, and 10, we want to count that this could be broom 2, right? So what we want to do is we want to multiply 4, choose 3 by the number of Comet 260s. 8 times 4, choose 3, right? So there you go. 8 times 4, choose 3. How many samples have at least 3 Comet 260s? So at least. This is a little bit different. So, okay. In that case, you could have, let's see. We want to, this is an OR criteria here. What if we had 4 Comet 260s? Then that's going to be 8, choose 4. Right? Those are all the cases. 8, choose 4. Okay, now we want to add that to if there's 3 Comet 260s. So it's, let's see, 8, choose 3, but then you could have one of the Nimbus 2000s, and that's going to be, there's 4 of those. So there you go. 25 crates of apples are delivered to a store. The apples are of 3 different sorts, and all the apples in each crate are of the same sort. Show that among these crates there are at least 9 containing the same sort of apples. Okay, 25 crates of apples, and each of the crates has a different sort. All the apples in each crate are of the same sort, and there's only 3 total sorts, though. So, show that among these crates there are at least 9. So we're going to be solving for C. We want to show that C is at least 9. So we should have N and K then. So it looks like N's going to be 25 and K is going to be, so there's 25 pigeons, and what are the pigeonholes? The sorts? So, okay, now let's just think about this and see if that makes sense. So you've got sort 1, sort 2, sort 3. 1, 2, 3. That's the, yeah. Now you've got the 25 crates, right? So the crates, you take a crate and you put it in a pigeonhole based on what sort it is. Take another crate, put it in a pigeonhole. And they're saying that, show that there's, once you're done, because each crate has to go in a pigeonhole, show that once you're done, you're going to have one of the sorts have 9. So there's going to be 9 crates in one of the sort boxes at the very least. Could be more, but you could have all of them be the same sort maybe, but at the very least you're going to have 9. So, okay, so we have to solve this. So we've got, let's see, 8 times 3 is 24. So this is 8 point something. That's 9. There you go. Lollipop Farm has cats, dogs, goats, ducks, and horses. How many ways can you select 3 pets to take home? Okay, so you're going to select 3 pets, right? And you can choose from cats, dogs, ducks, goats, horses. And it's repetition. You could choose 3 cats if you want, 3 dogs, whatever. And order doesn't matter. So this is just combinations with repetition. Simple problem. So you're choosing from a group of 5 for 3 slots. 5 plus 3 is 8, minus 1 is 7. 7, choose 3. 20 batteries will be put on the display. The types of batteries are AAA, AA, C, D, and 9 volt. How many ways can we choose the 20 batteries for the display? So it sounds like a combinations with repetitions problem. Let's just verify that. So I guess you could choose all AAA if you want, all AA. So it's like we're choosing from the, C, D, 9 volt. Okay, and then we've got these slots on the display. It's 20 batteries. Okay, but you can choose, it sounds like they're saying I could choose all AAA batteries if I wanted to. But the order doesn't matter. Unless, I'm assuming it doesn't matter. If it did matter, that wouldn't be a problem. You have to use permutations with repetition. So, okay, we've got, let's see, we're choosing from a group of 1, 2, 3, 4, 5 for 20 slots. 20 plus 5 is 25, minus 1 is 24, so 24, choose 20. How many ways can we choose the 20 batteries, but be sure that at least 4 batteries that are 9 volt batteries? Okay, so let's see. So at least 4 are 9 volt. So you've got 4 slots taken up by the 9 volts, so you're left with 16 slots to choose from the 5 batteries. You could choose all the rest be 9 volt if you want. It doesn't matter. So 16 plus 5 is 21, minus 1 is 20, so 20, choose 16. Okay, now how many ways can we choose the 20 batteries but have no more than 2 batteries that are 9 volt? So, okay, this is like an OR criteria. You've got, what if no batteries are 9 volt? Then you've got, we're choosing from 4 for, was it 20 slots? Yeah. So 23, choose 20. So that's the first case. Okay, but what if you have one 9-volt battery that leaves 19 slots? You're choosing from 4, or no? Yeah, choosing from 4, because now you can't choose a 9-volt battery. So that's 23, choose 19. So we can see the pattern here. So, okay, what if we have 2 9-volt batteries? That's 20. Wait. No. That's not right. 19 plus 4 is 23, minus 1 is 22. So this is 22, choose 19. And then now we've got 21, choose 18. And that's it. 10 students solved a total of 35 problems in a math Olympiad. Each problem was solved by exactly one student. There's at least one student who solved exactly one problem, at least one student who solved 2 problems, and at least one student who solved exactly 3 problems. Prove that there's also at least one student who solved at least 5 problems. So this sounds like a pigeonhole problem. There's at least, this that did this. At least, right? So, okay. The hard part is, what are the pigeons, what are the pigeonholes, and how many pigeonholes are there, and how many pigeons are there? That's the hard part. So, okay. Sounds like the students, well, no, you have 10 students, 35 problems, so I guess either one of those could be the pigeonholes or the pigeons. So prove that there's at least one student who solved at least 5 problems. So, okay, this is how we can do this. We've got let's say the 10 students are the pigeonholes. Okay? And then the 35 problems are the pigeons. So a problem has to go to one of the students. Now, no matter what, one student got one of the problems, who solved exactly one problem. So there's at least one student who solved exactly, each problem was solved by exactly, yeah, you don't have 2 students working on the same problem. So, that's just saying that each pigeon goes into one and only one pigeonhole. It doesn't get split up or anything. There's at least one student who solved exactly one problem. So what we can do with that is we can like erase this, ignore this, and just change this to 34, right? So that takes care of that. So now we've got these 9 pigeonholes and 34 problems, because that student didn't solve 5 problems, right? I mean, or this, we don't have to think about this. Okay, so there's at least one student who solved exactly one problem, at least one student who solved 2 problems. I'm assuming they mean exactly. They should have freaking put exactly if they meant it. And at least one student who solved exactly 3 problems. So this is kind of confusing. It's the at least, but the key word here to me is the exactly. The exactly. So there could be multiple students that solved just exactly one problem or 2 problems, but that's possible. But there's at least one student who solved exactly one problem. There's at least one student who solved exactly 2 problems. There's at least one student who solved exactly 3 problems. Exactly. At least one. So we can just erase these. 3, 4, 5, 6. So 35 minus 6, we're left with 29. Right? Now, it could be the case that maybe, so we're trying to account for the fact that it says the at least here. So maybe it is the case that this student only solved exactly one problem, and so did this student. And this student solved exactly 2 problems. So that's the only thing I'm a little confused about is, does this at least put another restriction on us, or do we have our pigeonhole problem figured out where N is 29 and K is 7? Or is there something else? Because it looks like if we did this, 7 times 4 is 28. So this is 29 divided by 7 is 7.8. something, so that rounds up to, or no, it's 4 point something. So 29 divided by 7 is 4 point something, so that rounds up to 5. And that proves it. But does this at least mean anything? No, it doesn't. It doesn't tell us anything, because it could be the case that since at least one student solved 1, 2, and 3, well, okay, we could be done with that. We already took care of the at least one for each of those. So all of the you could have none of these have 1, 2, or 3. You could have all, let's see, all 29 problems go to this student, the rest gets 0, and that still satisfies the criteria because still at least had 1, 2, or 3. Okay, and so if all 29 went to one student, then at least one student who solved 5 problems. Worst case scenario, you try and evenly distribute this as much as you can. You're going to have a case where all of them have 4, and you have 1 to go. So someone's going to have 5.